Okay, thank you very much. First of all, let me thank the organizers for giving me the opportunity of speaking here today, and let me also thank all of you for being here. I'm well aware that this is the very last talk of such a great event, so I promise I will try to keep it light, which means also that probably it will become boring. If you are too bored, please speed me up. Now, why I have chosen this topic? Mainly because I'm a categorical algebraist. So whenever I hear universal properties, this rings me a bell, which means adjunctions which can be promoted to equivalence of categories. Now, why for universal enveloping algebras? Because probably you have already seen universal enveloping algebras of Lie algebras. You are already familiar with these constructions. So I hope I will be able to say you something about what I do in context which is supposed to be your comfort zone. Now, even if this is not the case, I'm planning to start with a bit of warming up, which may require even half of this lecture, about ordinary Lie algebras over a field, which I will always denote by small k, and I will always assume to be of characteristic 0. So if you prefer, you may imagine that I'm working with the rationals, the reals, the complex numbers, it doesn't matter. Now, geometrically speaking, at this level, a universal enveloping algebra, it's a kind of differential, well, invariant differential operators on a Lie group. But if we want to study differential operators on a smooth manifold, which is not a Lie group, then we need something more general than a Lie algebra. And this something more general is what in the literature goes under the name of Lie-Reinhardt algebras. Now over commutative algebra A. Still, we have some geometric flavor. A can be understood as the algebra of smooth functions on a smooth manifold. This can be understood as vector fields on a smooth manifold. The universal enveloping is differential operators. But time permitting, I would like to break the wall, if you like, of naive non-commutative geometry and say a few words about the case of anchored Lie algebras over a non-commutative base. This is not strictly necessary. I'm much more interested in arriving at least at the wall of non-commutative geometry. If you have any question, please stop me. Don't worry. If I don't say anything about this, it's not a problem. At the end of the abstract, there are a couple of references to 2 archive papers of last year almost. If you are really interested in the non-commutative setting, you can have a look at them. Now, okay, let's do like this. Lie algebras over a field. Probably you know what a Lie algebra is supposed to be. It's a vector space with an antisymmetric bracket which satisfies the Jacobi identity. Probably you also know that if I take any associative and unital algebra over K, by the way, all my algebras without any adjective are associative and unital, otherwise I will call them differently. So if I take an associative and unital algebra, then I can look at A as a Lie algebra by taking the commutator bracket. And whenever I will do this, just to be sure, I will denote this by LK of A, by which I mean the Lie algebra associated with my associative algebra. Now, the first question is, can we do the converse? Given a Lie algebra, can we construct an associative algebra, and preferably in a meaningful way? By meaningful, I mean I want an associative algebra whose representation theory is the same as the representation theory of my Lie algebra. The answer is yes, and this is exactly what a universal enveloping algebra does. So a universal enveloping algebra for my Lie algebra L is an associative and unital algebra over K then I want this associative and unital algebra to be an enveloping algebra. So I want a Lie algebra map from my starting Lie algebra to the Lie algebra associated with the universal enveloping. So this is, well, over a field of characteristic 0, this is even injective. So that's why it's called enveloping. And now I want it to be also universal. Where by universal, I mean that if I have another associative algebra together with another morphism of associative algebras, then where to go? I may go here probably. Then there exists a unique homomorphism of unital associative algebras, which extends small phi. And by extending small phi, I mean that if I take here small phi, here I take my canonical eta, and here I take phi, then this diagram is commutative. Which in particular, it's telling us that whatever this universal enveloping algebra is, as an algebra is uniquely determined by the Lie algebra. Because any algebra homomorphism out of the universal enveloping is uniquely determined by how it behaves on L. Okay, secondly, this universal enveloping algebra is doing what we want, because probably you remember that a representation of a Lie algebra is nothing else than a Lie algebra map from L to the endomorphisms of some vector space. So this correspondence is telling me that any representation of a Lie algebra is a module over the universal enveloping and vice versa. Okay, I would probably be happy, but somebody may complain, this definition may be empty. I have given the definition of an object in terms of a universal property, so nothing ensures me that such an object exists. Luckily for me, it does. So the universal enveloping can be constructed, if you like, as the quotient of the free associative algebra, so this is the tensor algebra, mod out by the relations that tells me exactly that the canonical map is a Lie algebra homomorphism. Okay, I'm much happier, but still somebody can say, this definition is completely useless. This is a huge object, okay? It's a definition by generators and relations, but if we want to really manipulate this gadget, what can we do? Okay, let's see one probably of the most important results in the theory, which is the PBW theorem from Poincaré-Birkhoff-Witt. This dates back at the beginning of 20th century, which in human words is saying that the ordered polynomials in an ordered basis of the Lie algebra forms a basis of the universal enveloping. Or in a basis-free way, the graded associated to the universal enveloping of L as an algebra, it's isomorphic to the symmetric algebra over L. So just as a vector space, this is a kind of space of polynomials over a basis of L. Okay, just in case there's somebody in the audience who have never seen universal enveloping algebras before, a very quick example. If I take H to be the three-dimensional real Heisenberg-Lie algebra, then the universal enveloping of this is nothing else than the quotient of the algebra generated by CXP by the commutator relations between X and C, the commutator relation between P and C, and the fact that P acts on X as a derivation, giving back C. And if you have ever heard about Ore extensions of commutative algebras, this is nothing else than the Ore extension of the algebra on Cx by the derivation uniquely determined by the rule that delta of C is 0 and delta of X is C. Fair enough? Okay. Now, up to here, I have just spoken about the algebraic side of the universal enveloping and the algebraic universal property. But in fact, the universal enveloping algebra is much more than just an algebra. It's what is called a Bialgebra. Now, again, probably if you have already seen Bialgebras before, please tell me. Otherwise, let's see quickly what a Bialgebra is. So first of all, let me take a vector space over my favorite field. Then surely you will tell me that in order to have a K algebra, I need a K bilinear multiplication on B and a K linear unit, and this would give me an algebra over K. I will just slightly correct the definition by asking a linear multiplication, because in this way it becomes clear what I'm just going to add in a moment. I want to add two algebra maps, which are called the co-multiplication and the co-unit, simply because they goes the other way around.
Sorry,
yeah.
There is a question in the chat, which is, what is C?
Well, okay, it's one of the generators of the Heisenberg algebra, at least as far as I know. The H is the real vector space generated by C, X, and P, subject to the relation that the bracket between X and C is 0, and that's the same as the bracket by C and P, and then I want that, I want that Px is C. Okay? So, in order to have a bialgebra, I want to add two algebra maps. Yep. I may tell a joke in the meanwhile, so. This I called, algebraically, it's a particular instance of an OR extension. If just you want to Google something, that's the name of this gadget, which have also been called skew polynomial algebra. Okay, my managing of space on the blackboard is a nightmare. In the meanwhile, let me earn some time. Is it working right now? Still no? Oh, I mean. Okay, are we online again? Fine. In order to have a bialgebra, I want to add two algebra maps, which are called the comultiplication and the counit. I want them to be co-associative and co-unital. I mean, it doesn't matter too much. What is really important about bialgebras is the reason why we study them. Because having a bialgebra structure on an algebra means that the category of modules is monoidal with respect to the tensor product over K and the base object K itself, which I will show you after that the universal enveloping is a bialgebra, but the point is that if we take tensor product over K of representations, this is again a representation, and K itself, it's a representation of our Lie algebra. These are the consequences of having a bialgebra structure, and conversely, if we know this, then we know that our algebra is a bialgebra. Yeah.
Is there a compatibility condition between the algebra and the bialgebra structure?
Yes.
I didn't write it down, but...
The compatibility condition was a bit implicit in the fact that I asked delta and epsilon to be algebra maps. So I want delta and epsilon to be multiplicative in this case, which is what ensures us, I mean, you may imagine that delta is giving us the action on the tensor product, epsilon is giving the action on K, so being algebra maps tells us that this action is associative indeed. Now, if this is the first time somebody sees bialgebras, probably we want to see a few examples and at least a non-example of a bialgebra. The easiest example is the group algebra with the delta uniquely given by delta of G equal G tensor G and epsilon of G equal 1. This is pretty easy, it's given on a basis, so we're happy. The second one probably is slightly more complicated. The coordinate algebra of a fine algebraic group where delta and epsilon are induced by the multiplication and the unit on G. Probably a bit more interesting, it's the algebra of representative functions on a Lie group. This is, again, a bialgebra where delta of a function is of the form some gi tensor hi, if and only if f of xy is the same as the sum gix hiy, and epsilon of f is given by evaluation at the unit of G, which may look like a bit strange, but imagine for a second that our Lie group is the real numbers with the sum. Then, for instance, I can tell you that delta of the exponential map is exponential times exponential. I can tell you, for instance, that delta of sinus is cosinus tensor sinus plus sinus tensor cosinus, or even better than delta of the cosinus is cosinus tensor cosinus minus sinus tensor sinus. Just to have. Oh, no, it's sum of indices, because in principle delta of something lives in the tensor product. So it may be a sum of some pure tensors. I mean, in general, I'm not even writing it in terms of a basis, as a linear combination of a basis. In Hopf algebra theory, we even write it formally using the Hennemann-Wheeler segmentation.
So I runs over what?
It's a family of indices running from some 1 to some t, which depends on f. So for instance, since we know that the exponential of the sum is the product of the exponentials, Then for the exponential, the sum is one single summand, which is exponential tensor exponential. For the sinus of the sum is sinus of the first, cosinus of the second, plus cosinus of the first, sinus of the second. So in this case, I is run over just two elements. For the cosinus, again, it's just running over 2. For delta of a basis of the group algebra, it's again just one pure tensor. And for the universal enveloping, so let me give a slightly more complicated example, if you like. The universal enveloping is a Bialgebra where delta of x is x tensor 1 plus 1 tensor x, epsilon of x is 0 for every x in the Lie algebra. So for instance, delta of xy, in this case, it's xy tensor 1 plus 1 tensor y, plus x tensor y, plus y tensor x, plus 1 tensor xy. So here we have 4 summands. Essentially because delta is an algebra map, so this is delta of x times delta of y, and it gives exactly this one. So in principle, there is no fixed length for a delta. Now, you may imagine that if here I put an arbitrarily long monomial in elements of L, this becomes an arbitrarily long sum, but always finite. Okay, and my favorite example is a non-example, the first Weil algebra. This may sound a bit curious because the first Weil algebra is a kind of algebra of differential operators. I'm saying that a universal enveloping is a kind of differential operator, so why the Weil algebra is not universal enveloping? Simply because asking epsilon to be an algebra map means that the kernel of epsilon is an idea, and the first Weil algebra is a simple algebra, it has no ideas. So there's no way to convert the Weil algebra into a K bialgebra. We will see that it is something slightly more general than a K bialgebra. Oh, now, why speaking about bialgebras? Because the universal enveloping is universal also as a bialgebra. Let me state it like universal property again. The point is that, first of all, for any bialgebra over K, we can consider the space of primitive elements of B, and this is the vector space of all those B in B, such that delta behaves on B as it does on the elements of the Lie algebra in the universal enveloping. These are called the primitive elements of my bialgebra, and this is a sub-Lie algebra of the Lie algebra associated with B. So the commutator of two primitive elements, it's again a primitive element. Second observation is that the eta that gives the universal property of the universal enveloping is in fact landing in the space of primitives of the universal enveloping. And third is the true universal property. So for any Lie map landing in the space of primitive elements of some B, there exists a unique morphism of bialgebras deep psi from UL to B, which once restricted to the space of primitive elements gives back the psi we started with. Oh, okay, so if you have been exposed to category theory at least once, you will start feeling that here some adjunctions are in play, because whenever I have a universal property of this form, then you may recognize that both UK and PK are functors. This eta is called eta because it's the unit of some adjunction. Probably there's a co-unit hidden somewhere. That's indeed the case. And in this case, so Lie algebras versus Bialgebras, this adjunction can be even promoted to an equivalence. This is probably one of the most important results in the structure theory of Bialgebras. Is the celebrated Milnor-Moore theorem, which dates back to 1965, and which is telling us that Bialgebra B is the universal enveloping of its space of primitive elements, if and only if, now we will state it as they were stating it, B is primitively generated. By primitively generated, I mean it's the smallest algebra containing its space of primitive elements. This can be equivalently stated by saying that B is co-commutative and it's filtered, and the smallest component of the filtration is the base field. Okay, there's another half of this theorem, which is in fact a consequence of the Poincaré-Vilkovisky theorem, which is telling us that any Lie algebra is the space of primitive elements of its universal enveloping. So as I was telling you, here we have two factors which are quasi-inverses one of the other. So in fact what I have just wrote on the blackboard is the fact that the category of Lie algebras over K is equivalent to the category of primitively generated Bialgebras over K, which may sound completely abstract nonsense, but from the point of view of people working in Hopf algebra theory, this is the third theorem for Lie algebras. Because a bialgebra, so actually the finite dual of a co-commutative bialgebra is a commutative bialgebra. In fact, here we are working with Hopf algebras. So it's a commutative Hopf algebra, and commutative Hopf algebras are essentially representative functions on Lie groups. So this theorem is essentially saying that there's a way to assign, in a very fancy way, a Lie group or something that looks like a Lie group to any Lie algebra and vice versa. Okay, now next level. This was more or less classical. As you see, probably the most important theorem dates back to 1965. So let's do the next step, and let's pass to the Lie-Reinhardt case. Now let me try to go a little bit slower. So first I give the definition, then I explain the definition. A Lie-Reinhardt algebra over a commutative algebra A is the following. It's simply an ordinary Lie algebra over K, but together with an action of A, so it's not just a Lie algebra, it's also an A module, and it comes also with a Lie algebra map that we call the anchor landing in the space of derivations of A, such that omega is a linear, and here is really fundamental that A is commutative, otherwise the space of derivations is not an A module in general. So no compatibility with an action if A is not commutative. And I also want a Leibniz-like rule. So I want that if X is acting on a Y, this has to be the same as X acting on A times Y plus A dot X acting on Y. This is the algebraic abstraction of the vector fields on a smooth manifold. That's probably the archetypal example. If A is the commutative algebra of smooth functions on a smooth manifold, and L is the Lie algebra of vector fields, then we know that we can act with a smooth function on a vector field. This omega is the identity because this is exactly the space of vector fields. And the Leibniz rule is the well-known Leibniz rule that we study in any course of differential geometry. In fact, the space of global sections of any Lie algebroid is again an example of Lie-Reinhardt algebra, but in principle, this definition is more general because there's not written anywhere that L needs to be finitely generated projective. Now, Lie-Reinhardt algebras in the second part of this picture are taking the place of Lie algebras. We also have something that takes the place of K algebras, and this something are the so-called A rings. And A ring is some A bimodule. Now, if I'm lucky, okay, it's still there. That's the definition of a K algebra. Now look at the definition of an A ring. This is a bimodule over A, together with an A balanced bilinear multiplication and an A bilinear unit, which are associative and unitary. So it's the analog of a K algebra, but over an arbitrary commutative ring, and observing that A is not necessarily landing in the center of R, as it's happening for K algebras. So here we have really bilinear multiplication and unit, and this is really A balanced and not A bilinear. Okay, now, for A rings, also we have a way of associating Lie-Reinhardt algebra. So the point is that for any A ring R, we can consider a Lie-Reinhardt algebra that I denote by LAR. Now, informally, this is the space of all those elements of R which acts as derivations on A. Formally, it's the space of all those R delta living in R times derivation of A, such that R acting on A, so the commutator between R and A is the same as acting with delta on A for any A. Now trust me, this is a Lie-Reinhardt algebra over A, and the universal enveloping, and we have a universal enveloping in this setting as well, in the sense that we would like to have a construction as we had before. So we want to assign an A ring to any Lie-Reinhardt algebra in a universal way so that the representation theory is always the same. Why we would like to do so? That's what Niels told us on Monday. Probably we want to speak about homology and cohomology of Lie-Reinhardt algebras. We are too lazy to do everything from scratch again. So we substitute the Lie-Reinhardt algebra with an associative algebra, and we use the fact that we already know how to compute cohomology of associative algebras. So no need to do everything from scratch. As we have done before, let me give you the definition. So a universal enveloping algebra for my Lie-Reinhardt algebra L is, first of all, an A ring, which is enveloping my Lie-Reinhardt algebra, as we were doing before, and that's not all. We also want it to be universal among all the A rings which are enveloping my given Lie-Reinhardt algebra. So for any other psi, for any other phi, there exists a unique psi of A rings from the universal enveloping to R, which is extending phi as we were seeing before. Now, usual problem, in principle, this can be an empty definition, but I'm lucky again. This is not an empty definition. This theorem has actually many authors, if you like, many contributors. The original construction is due to Reinhardt himself in 1963, but the first proto-version of a universal property appears in a paper by Malyavin in 1988, and he's referring even to an elder paper, but the universal property of the universal enveloping and the construction we are going to see right now is due to myself at the beginning of this year. In particular, the construction of this LAR is completely new. I have no idea why nobody noticed that before. So, the universal enveloping algebra of my Lie-Reinhardt algebra can be realized as the tensor, the A tensor algebra now, over the tensor product of L with A, because I really need an A by module here, modulo a bunch of relations that I don't want to give into the details because are just annoying, bothering algebraic relations. But they are very similar to the ones that we have for the universal enveloping of the algebra. So, it's time for a pair of examples, at least. At the end of this nice week, I just feel like a toy mathematician, so I will give just a toy example, a couple of toy examples. The first one is the example I promised at the very beginning. The first wave algebra, now it's an example. Why? Because it's the universal enveloping algebra over the algebra of polynomials of the Lie-Reinhardt algebra generated by the total derivation by x. So it's an algebra of differential operators. Second example, the universal enveloping algebra of the Heisenberg algebra we have seen a moment ago. It's also an example. This is as K algebras and nothing else, but it's also an example of a universal enveloping in this sense, because it's the universal enveloping over the algebra of polynomials in two indeterminates of the Lie-Reinhardt algebra generated by the delta that was written somewhere there before. So this is the unique delta sending C to 0 and X to C. In fact, if you are really interested, any other extension of a commutative algebra with trivial sigma give rise to an example of a universal enveloping, but if you have never seen other extensions before, it doesn't matter. Oh, okay. Again, same problem as before. We have a definition, we have a realization. What we can do with the realization, that's again huge object. As we had for the classical case, here we have Reinhardt's PDW theorem, which is telling us that the gradient associated to the universe, under the hypothesis that L is projective, because this is not for free. So the gradient associated of the universal enveloping is the symmetric algebra over L, which in human words is saying that the ordered monomials in an ordered set of projective generators of L as an A module is giving a set of generators of the universal enveloping Please be careful, this is not free. In general, this object here is not free over A, so we cannot speak about basis, but at least if we want to do computation, we know how to write a general element in the universal enveloping somehow. Yes, all of this was again concerning the algebra structure of the universal enveloping, but now it's time to see the further structure of the universal enveloping. As we had for the universal enveloping of a Lie algebra, the universal enveloping of a Lie-Reinhardt algebra, it's something more than just an algebra. It's what Niels showed us on Monday, a co-commutative bialgebroid over our base. I will be speaking about co-commutative bialgebroids because they are a very particular example of a bialgebroid. Not every bialgebroid is co-commutative, and the definition of an arbitrary bialgebroid is really a nightmare. So if I may avoid giving it, it would be much happier. What is important is that a co-commutative bialgebroid, okay, let me state it like I will present it directly as a universal property for free. So the point is that the universal enveloping algebra is a co-commutative bialgebroid. I know that you know what a Lie bialgebroid is. Please, for the moment, refresh completely your mind. The two notions are related, but they are definitely not the same. A Lie bialgebroid is the Lie analog of what we're going to see, but what we're going to see is the algebraic construction of a algebroid, of a bialgebroid. This is simply an AD ring, so the structure we were seeing a moment ago, plus a co-multiplication over A now, which is co-associative and co-unital, plus compatibility conditions. The problem is that the compatibility conditions are much worse than those we had before. Again, delta is multiplicative in some sense, epsilon is a kind of character on our universal enveloping, but the point is that this is not an algebra in general, so there is no way to give a nice formulation of these compatibility conditions. Let me just tell you that the importance, so everything you see here is the algebraic counterpart of the statement. The category of UL modules is monoidal with tensor product over A and A as a base object. And since the category of modules over the universal enveloping is the same as the category of representations of a Lie-Reinhardt algebra, this is telling us that tensor product over A of representations is a representation again, and that A is a representation. So this is the important message to bring back home. Bialgebroids are designed to have this property, full stop. Now, for bialgebroids, again, we have a notion of space of primitive elements, and the eta we had before is in fact landing in the space of primitive elements of the universal enveloping, and the universal property is always the same for every morphism of Lie-Reinhardt algebras landing in the space of primitives. There exists a unique extension to a morphism of bialgebroids from the universal enveloping, which extends the given. And as we had for the universal enveloping and the space of primitives in the classical case of the algebras, we can promote this universal property to an equivalence of categories. And with this, I believe I will conclude, because otherwise we have already run out. I'm already running out of time. Okay. So as I was saying, also in this case, we can promote everything to an equivalence of categories, and this has been done 11 years ago by Moerdijk and Bertschulin, who proved the following version of the Miller-Moore theorem. This is Moerdijk and Bertschulin, 2010, for a co-commutative bialgebroid over A. Oh, by the way, co-commutative simply means that delta is commutative. If you want more details, I can give it to you, but that's just a commutativity property for the delta. So for any co-commutative bialgebroid, we have that B is the universal enveloping of its space of primitive elements. If and only if, first I write, then I explain, well, actually I translate it for you. B is co-complete and graded projective. Now, co-complete is just a fancy way to say primitively generated. This is the smallest algebra containing its space of primitive elements. Graded projective is slightly more complicated. The point is that in order to have the PBW theorem, we need the Lie-Reinhardt algebra to be projective. So we need here to have a bialgebroid whose space of primitive elements is projective over A. But if the space of primitive elements is projective over A, the PBW theorem is telling us that the universal enveloping is projective, its graded associated is projective, and this is what graded projective means. That the graded associated to this bialgebroid here is a projective A module. So in particular, every direct summand is a projective A module. The other half of the theorem, it's again a consequence of PBW, and this is telling us that if L is projective, which was the hypothesis of Reinhardt-PBW theorem, then L is the space of primitive elements of its universal enveloping algebra, which put together, it's telling us that projective Lie-Reinhardt algebras over A is equivalent to the category of co-commutative bialgebroids over A, which are co-complete graded projective, which from an OIT point of view, it's a kind of Lie-third theorem for Lie-Reinhardt algebras. To any Lie-Reinhardt algebra, we can associate something which is related to something which looks like a Lie groupoid. 2 seconds of advertising. We have seen 2 different photos of the same picture. We have an object, which is Lie something, we have the universal enveloping, which is associative something. It has a universal property. The universal property gives a bialgebroid something property. It's universal with respect to that. And we have an adjunction at the algebra level, an adjunction at the bialgebra level, and the adjunction at the bialgebra level can be promoted to an equivalence. You may imagine that the third part of a non-commutative algebra would have been, okay, we have anchored the algebras, we can construct a universal enveloping. The universal enveloping is explicitly given by the Kohn-Moscovici bialgebroid construction. That's an algebra, it's universal, it gives an adjunction, it inherits a bialgebroid structure, it's universal, it can be promoted to an equivalence. End of the advertising.
Questions?
You did not pronounce the word quantum groups. Are they somewhere behind these constructions?
Yes, I mean, the universal enveloping of Lie algebra is an example, it's the easiest example of a quantum group. Then we have Greenfield deformation of the universal enveloping, which goes to the ordinary quantum groups. If you like, the universal enveloping of Lie-Reinhardt algebra is a kind of quantum groupoid. I don't know if we have a deformation theory for this, probably Niels no. Okay, he's saying he's nodding, so yes, we have a deformation theory. We have quantum groupoids in the true sense, but in some sense this is the naive side of quantum groups, because up to here I just use algebraic properties and I use categorical properties. I never introduce topological properties, sister algebras considerations, and so on and so forth. So quantum groups are not that easy. When I need to present this to people, I usually say, okay, Hopf algebras are quantum groups. It's not that easy, but almost we are there.
The questions? So your advertisement about your generalization. So do you have an example in the non-commutative algebra case? Like, I don't know, like the analog of differential operators on a non-commutative manifold or something else? Your favorite example, you say?
I don't have presently anything that elaborated, because working over a non-commutative something, it's difficult to say what a differential operator is and over what it is, because I don't have underlying manifolds or anything. I don't have an underlying geometric space on which I can describe the differential operators. I can give a kind of toy example, which is probably my favorite handable example during a presentation at the blackboard, which is the following. Let me take as A the algebra of n times n square matrices over a field, and let me take as B the algebra of k-linear endomorphisms of A. I know it's completely not clear presently why, but since this is finite dimensional, this becomes non-commutative, non-cocommutative Bialgebroid over a non-commutative base. This is the completely opposite of a universal enveloping we are used to. In this setting, I can still consider the space of primitive elements of this B as a Bialgebroid.
And the coproduct, what do you?
The coproduct is using the fact that since this is finite dimensional, I can give essentially the same coproduct that we have for Lie groups. So I define
The dual of the product.
yes, it's the dual of the product essentially. If you like, it's connected to the fact that this can be written as MNK tensor MNK star, and yeah, it's the dual of the product. I can write it down the details, but not now, because I'm trying to remember what are the primitive elements. The primitive elements, if I'm not wrong, are exactly the space of k-linear derivations of M and K, which by Stirling-Noether are just the inner derivations, which means that I didn't write down explicitly the construction of the universal enveloping in this case, but the universal enveloping of this space of primitive elements is the Kohn-Moscovici Bialgebroid over the universal enveloping algebra over the zero Lie algebra. And in fact, this Bialgebroid here, it's satisfying the equivalent of the Milnor-Moore type theorem. So in fact, this universal enveloping algebra here is exactly isomorphic to B as a Bialgebroid. I know it's slightly trivial, because if you go and write down explicitly what this object is, it's exactly this object here. So I'm somehow close the circle. But yes, this is the toy example.
Thank you.